So we've been talking about alcohols here. We got into naming alcohols. We got into a little bit about some of the reactions last time. Reminder again, when we talk about alcohols, it is the functional group that's the OH group, kind of the hydroxide group there. That is the functional group that we have for an alcohol. That OH group is a polar group, just like we talked about when we talked about with bonding, oxygen being more electronegative than hydrogen, creates this sort of polar group that's on an alcohol. And that really does give some alcohols some solubility in water. Kind of 6 or less sort of carbons attached there. It's able to interact really well with water through that OH group because it's essentially the same group that you have going on in water. And it's able to do that hydrogen bonding, like we talked about last time, I believe. So hydrogen bonding, which is that intermolecular force between, say, the alcohol and the H. Again, kind of smaller sort of alcohols, really sort of soluble there in water because of that, because of the presence of the OH group. But solubility definitely starts to decrease a lot with water as we sort of build out the carbon side of the alcohol molecule. So, the more sort of carbons you got attached to this side, the less and less sort of soluble it sort of becomes. Remember that when we name alcohols, it's pretty much just like what we normally do with everything else. We're looking for the longest carbon chain. And the key with this one is because of that OH group, we do need to make sure that the OH group is part of that longest continuous carbon chain. That will make us the base of the name one of those alkanes. We'll drop the last part of the name and put OL at the end of it. Again, just like an alcohol, OL, in terms of that. Also very similar to what we do with our double bonds and triple bonds. We do need to give the location of where that OH group is located. Again, especially when there's sort of more than one option as to where that OH group can kind of end up. And in terms of alcohols, that usually means that we're looking at about 3 or more carbons at that point is really where you start to get an option as to where that OH group could be located. That's again why when we look at something like this, which is methanol, there's no need for a numbering because there's really only one carbon, only one spot where that could be. Even with ethanol, which is our 2 carbon guy, again, there's no need to give the numbering of it because remember, this guy here would get the priority in terms of the numbering, which means, if you put it on the guy on the right, like I did here, that would be carbon 1. Even if you kind of flipped it around and had the OH group on the other side, you would just number basically the opposite way. And this would still be carbon number 1 where it's located. So even though you could kind of draw it on the left side, right side in this particular case, you can, there's really only one spot for it. But when we do get to those kind of 3 carbons in a row, or 3 carbons, we could have our OH group over here. And this would be 1 propanol, again, the 1 being where the OH group is located, carbon number 1. We could also, in a row of 3, put the OH group in the dead center there and end up with this here. It's a very bad looking H. This would be 2 propanol. Again, location here, carbon 1, carbon 2, no matter which way you go, 1, 2. So because there's a couple different options as to where it could be, that's when we need to start giving the location. Again, very much like with our double bonds or triple bonds. Alcohols like 2-propanol. Also, if you recognize sort of the group on the bottom there, this is that CH3, CH3 group. That's that isopropyl group, which is why this is also sometimes called isopropyl alcohol, also known as rubbing alcohol as well. So a few different names in terms of what you could come up with. This again is more of the IUPAC name, kind of that official way of naming. Same thing here with our 1-propanol. Remembering that we do give the OH group the priority, which means once you establish sort of which way you're going to number the carbons, if there happens to be other groups attached, they're numbered accordingly. So for example, if I just slapped in a Cl there, and maybe drop that to a 2, because this guy's carbon 1, that would mean that would end up being 3-chloral 1-propanol. Again, we lock in that sort of numbering for the OH group, and if there happens to be somebody else there, then we would number accordingly like that. We also talked about, again, ways to classify alcohols. You could classify alcohols based on the number of carbons that's attached to the carbon that has the OH. That's a mouthful what I just said there, but basically this is the carbon that has the OH group attached to it. And again, attached directly to that carbon is one other carbon. This would be a primary alcohol. Here, looking over here, this would be the carbon that has the OH group attached here. Attached to that guy is 1 carbon, 2 carbons. This would be a secondary alcohol. And obviously you could have an alcohol such as this, for example, where the carbon that has the OH group is now attached to 1, 2, and 3 carbons, and this would be a tertiary alcohol. Question on that stuff there.
So, Professor, the 3-chloral 1-propanol, that would be a primary?
This one, it would be a primary. Looking at this carbon, it's attached directly to one other carbon, so it would be a primary alcohol, yes.
Okay, thank you.
You're welcome. Other questions? So, in addition, we started talking about some reactions, obviously, that involve these alcohols. I think I got another empty page here. Yeah. So we actually started last time as well talking about how we make an alcohol. So a reminder that we really do make an alcohol, for example, from adding water, a hydration reaction of an alkene, right? So we have this double bond, and when we add water, which is this guy right here, we're basically doing an addition reaction. So as we talked about a number of times last time as well, remember it's just this part that changes. And when we do this addition reaction, as we talked about, pretty much nothing else changes other than we're going to turn that into a single bond. So we talked about the idea that you pretty much have the structure in front of you. You just need to change that one part, which is what I just did there. I made my double bond into a single bond. We also talked about the idea that when we add hydrogen and something else in this type of reaction, this is what is referred to as an unsymmetrical addition. And the hydrogen always ends up at the carbon that had the most hydrogens to start with. So in this particular case, if we look at this carbon, it has 2 hydrogens. If we look at this carbon, it only has 1 hydrogen. That means that when we add this on, we should add the hydrogen to the guy on the right, as he had more hydrogens to begin with. The other guy would get our OH. So really here we go from 1, 2, 3. So this is propene, really, to our 2-propanol over here. Again, with the OH group, the OH at the end of the name here. This again is what is referred to as a hydration reaction. And when we do a hydration reaction, the opposite of that is another reaction that actually alcohols basically undergo. And this is what is basically referred to as a dehydration reaction. And in a dehydration reaction, we're basically removing water, is basically what that means. So if we just, yeah. Question?
I have a question. Can you tell me again why the OH doesn't go at the end of 2-propanol? Why does it go on the bottom of
Are you
that?
asking? Are you asking why the OH ends up on this carbon and not the carbon that's over here?
Yes.
Yeah, yeah. So there's a rule which is technically known as Markovnikov's rule. Very badly pronounced name there, but basically the rule is when you're adding something like this in an alkene of hydrogen and something else like water. We also talked about like HCl or HBr. So basically, you're going to add hydrogen and some other guy in with hydrogen. There's a rule that says that the hydrogen that's coming in will always end up at the carbon that originally started with the most hydrogen. So
Okay.
if we look at this guy originally, he had 2 hydrogens versus the other carbon in the double bond. And we're talking about the carbons in the double bond. Um, this guy had only 1 hydrogen. So the rule is the hydrogen will always end up at the guy that started with the most hydrogen. And that by default would mean in this case that the OH would end up on the other carbon. And the same thing would happen if we're adding HBr, the Br would end up where the OH is, and the Cl would also end up where the OH is as well. And that's just sort of the rule that you follow whenever you're doing these unsymmetrical additions of alkenes, adding hydrogen and something else.
Okay. Thank you.
You're welcome. Other questions? Now, the dehydration reaction is really the opposite of it. So if we just even take the one we just made up there, we're really just going to take away the water. And the way that we take away the water is we take it away the exact same way that we basically added it. And what we mean by that is definitely going to be a hydrogen and an OH, right? So an OH group and a hydrogen. So the OH is pretty easy to determine. We're going to take away that OH group. Now, if you remember, when we put it on, the hydrogen and the OH group are not put on the same carbon. They're put on opposite carbons, right? Or a carbon next to it. So in this particular case, we would actually take off a hydrogen from, you could actually pick any hydrogen you want in this particular case. And the reason for that is if we look to the right on this carbon, there's 3 hydrogens, right? If you look to the left on that carbon, there is 3 hydrogens, which means technically speaking, you could take any one of those hydrogens off, and that would make your water. Now, there is a rule, just like there's a rule we just talked about where we put the hydrogen on. If there's an option, in this case, there's not. So on the right here, we have 3 hydrogens. On the left here, we have 3 hydrogens, exact same number of hydrogens on the carbons that's next to the OH group, basically. Now, if there's an option that when you look at it, like for example, here's my OH, and say this carbon has like 3 hydrogens, and the carbon over here has only, say, 2 hydrogens, for example. What would happen in this particular case is we would actually take the hydrogen off of the one with the least. So it's kind of the opposite rule. We take it off the one with the least number of hydrogens. So when we put it on to make like the alcohol, the hydrogen goes to the one with the most. When you need to remove a hydrogen to basically dehydrate it, you take it off the one with the least. So they're kind of opposites of each other in terms of that. What I'm talking about here in this case is there's no difference really because there's 3 on the left, 3 on the right. So you could do it from any one of those carbons. So I'm just going to take the hydrogen right here. And when I do that, what that's going to get me is this reaction here that forms water. And again, that's formed from those parts that just came off, basically, in the yellow. And then what are we left with in terms of the structure? Well, just like the other stuff, we want to just copy it exactly the way it looks. So again, I'm not going to change anything other than I'm going to take off those 2 things, the OH and the hydrogen. So if I do that, right, something like this. Now, when we put the water on above, we did it by breaking the double bond to make room. But now when we take away the water, we're in trouble because we don't have enough bonds. So we actually, in this case, are going to put the double bond back in between the two carbons that we removed those sides from. So we removed it from here. We would put the double bond back in. That now gives everybody the proper number of bonds in that particular case. So hydration, put the OH group on. If there's an option, the hydrogen always goes to the one with the most. And again, if there's not an option, then you can put it on whichever side. And in a dehydration, we take the water off, and that brings us back to an alkene here. Question on that there. Now, we also were talking about reactions involving alcohols, which are really reduction and oxidation reactions or redox reactions. When we talk about oxidation, it implies three sort of definitions. One is losing electrons, which is typically what we think about in sort of non-organic conditions. Two is gaining oxygen as you go from reactants to products. And three is losing hydrogen or H2 as you go from reactants to products here. And reduction is pretty much the opposite definitions. Reduction means that you gain electrons. I'll learn the number here today. We gain electrons. In terms of organic chemistry, that means that you lose oxygen as you go from reactants to products. And the one that we see a lot is actually the gaining of H2 as you go from reactants to products. So these are the very common reactions that actually alcohols do undergo. And I think we got to talking about with everybody here primary alcohols. So let's take a look at a primary alcohol and sort of what happens when we look at a primary alcohol. And actually, let me draw it this way. We'll do this and kind of draw it out. We'll do this. We'll do this. And this is our, again, primary alcohol. When we do an oxidation reaction, sometimes they just put like a little O in some brackets, and that basically stands for oxidation. And the definition of oxidation that we're going to use in these sort of alcohol reactions is actually the loss of H2. So where do the H's come from? When we're dealing with alcohols and these oxidation reactions, the most important part of the molecule here is the carbon-oxygen bond here. So it's all about the carbon-oxygen bond. And when we go through a oxidation reaction involving an alcohol, what happens is we always lose the hydrogen off of the OH group. So this guy is always the one that comes off. So that's like half of what we need. The other hydrogen comes from the actual carbon. And again, you can take off either hydrogen on that carbon. I'll just take off the bottom one. And when we do that, that is where we produce H plus or hydrogen gas, H2, which is hydrogen gas. And what are we left with? So again, making these sort of reactions not super complicated, we really just draw everything that we have on the left-hand side. Obviously, the only thing that we take out are the two hydrogens that we boxed. So if I do that, again, I'm just going to copy it exactly the way it looked down to my carbon and oxygen bond and my H. Now, at this point, we have a very similar sort of idea, which is I took out two hydrogens. That means I need to put back in a bond. And basically what will happen is we will now get a double bond between the carbon and the oxygen. So we basically take off a hydrogen from the OH group. We take off a hydrogen from the carbon that has the OH group. And then we put a double bond between the carbon and the oxygen. And everything else remains the same. So again, as we talked about, there really is only one part of these molecules that really do change, and that's the only part you should adjust. Everything else should basically remain the same. Now, what do we go from? We go from a primary alcohol here to what is known as an aldehyde. And an aldehyde is another organic chemistry group that we'll talk about later on in this chapter, but it has the functional group of a carbon oxygen double bond with a hydrogen, and that is what we see here at the end. That is this group right here. By the way, just a preview of naming. This is ethanol. This guy also has 2 carbons. This is ethanol, actually, Al. So also based off of ethane and so forth. Question on that reaction there that we kind of talked about the other day. And again, it doesn't matter if, you know, there's 1 carbon or you got just a ton of carbons attached, really. You know, you got something like this. You know, sometimes people see something like this and go, oh, it's got to be more complicated. There's a lot more junk on there, right? But it really isn't. If we're going to take this through our oxidation, we can again recognize this as a primary alcohol. So we know that it is only this part right here is where our change is going to be. And again, we're going to take out a hydrogen from the OH. And you really can choose whichever hydrogen you want here. Either one of these 2 is perfectly fine. We're going to take off the H from there. We're going to produce that H2 and then just going to copy what's there. So carbon, carbon, carbon. We got some hydrogens. Got some hydrogens. Still got some hydrogens. Then we got a couple more there with some hydrogens. And then we get to our carbon oxygen, which we draw. We obviously lost the hydrogen on top, the hydrogen on the bottom, but still have the hydrogen right there. And now we know the last thing we should do is make a double bond right there. And we would slap in our double bond at this point. And again, between the carbon and the oxygen. Any questions on that one there? So always happens the same way. Oxidation or primary alcohol always end up with an aldehyde in this case. And it is just that 2 things that happen. H from the oxygen, H from the carbon that has the oxygen attached to it, double bonded up, and everything else stays the same. Any questions?
Can you quickly go back to the last slide that has the oxidation and reduction? That really quick, sorry. Thank you.
Other questions?
Thank you.
You're welcome. Okay, so we've been talking about the oxidation of oxidation of a primary alcohol, and again, that's how we get to our aldehyde. So this is the one we actually just did. So I'll put the step that happens right before that there, which was this. So this is essentially what we just did. Now, again, this is the definition, as we talked about, of losing H2. When we get to the aldehyde, it actually can go through an oxidation as well. So it can get further oxidized. So this guy at this point can then continue on that process of oxidation. The difference, though, is when we get to this part where it goes from an aldehyde this is what is known as a carboxylic acid, is the definition here for oxidation that we're going to talk about is actually the gaining of oxygen. And again, the absolutely positively only thing that is different between this aldehyde and this carboxylic acid is we slapped an oxygen right there. That's the only thing that's different. If you look at the molecule to the left, that is an H, a C, and an H, CH3. That is exactly the same. That's a carbon with an oxygen double bond. That's a carbon with an oxygen double bond. Heck, there's even the H still there, over there. The only difference is we basically added the oxygen, which again is another definition of oxidation reactions, is the gaining of oxygen. There's actually a lot more that happens to insert the oxygen that's beyond our class that we don't talk about, but the way you could simply think about it is we go from an aldehyde to a carboxylic acid. Carboxylic acid is another organic group. It has a functional group of carbon oxygen double bond and an OH group. So this is the functional group for carboxylic acid. Any questions on that there? So if we start all the way back over here with our primary alcohol and we do an oxidation reaction, we will end up with an aldehyde. If you decide to further oxidize it, you will end up with a carboxylic acid. So this primary alcohol shoots right through and kind of goes through a number of different reactions and can eventually end up all the way to the carboxylic acid. But if you just sort of do one oxidation, you stop there at the aldehyde. So let's talk about what happens with a secondary alcohol. Secondary alcohols such as this guy, and again, it also will go through an oxidation. It is the same deal. If we look at this carbon that has the OH group attached, it has one carbon there and two carbons there, and that's why this is a secondary alcohol. It's attached to two carbons. Again, the carbon that has the double bond. So what's going to happen here is exactly the same thing as what happens with a primary alcohol. It is again the carbon oxygen part. That's the important part. And just like we did on the previous one, we're going to take off a hydrogen from the OH group. We're also going to take off a hydrogen from the carbon that has the OH group attached, and we're going to make a double bond between the carbon and the oxygen. Exact same three things that we did on the previous one is the exact same three things that we would do with this guy. And again, if we look at it here, we're going to take off this hydrogen and we're going to take off this hydrogen. And when we do, nothing else changes on the rest of the molecule. It is still basically the same. Again, a carbon with three hydrogens, a carbon with three hydrogens. Other side, carbon with three hydrogens, carbon with three hydrogens, and our carbon oxygen right there in the middle, and our carbon oxygen became a double bond in this particular case. Not pictured here, but you would also get the H2 that would come off again from the two hydrogens that came off in this case. When we oxidize a secondary alcohol, we end up with another organic compound, which is known as a ketone. And the functional group for a ketone is basically a 3-carbon run in a row. And on that center carbon, you have the carbon-oxygen double bond. So this is the functional group for a ketone. By the way, at this point, unlike the aldehyde, no more oxidation happening at this point. It will not go through any more oxidation. It's actually missing a hydrogen to do that oxidation, so it cannot do it. So here, secondary alcohol, if we oxidize it, gets us to a ketone. The exact same thing happens as we've been talking about. those guys basically get removed. Doesn't matter if there's a bunch of other stuff on each side. You just kind of continue that process. So if we look at another sort of example here.
So Professor, the only difference is it's from a primary alcohol to a secondary alcohol. So that always stands. A secondary is a ketone, and then a primary goes to an aldehyde.
Exactly. So that's exactly what you get on the oxidation of your primary alcohol. Always will yield you an aldehyde. The difference is in a secondary alcohol, you'll always end up with a ketone. And the real reason why it ends up that way is a primary alcohol. Wherever my guy went, where my guy go? Here we go. Our primary alcohol, we kind of think about where the location of the OH group is. It's at the end, basically the carbon kind of makes it the primary alcohol. So because of that, when that double bond happens, you always end up with this aldehyde group at the end. Different is, in order for it to be a secondary alcohol, like what we're doing here, it's got to at least be inside. It cannot be at the end, the OH group. So it's like this one is in the middle carbon. And because of that, the only sort of carbon oxygen group that you can make is always going to be a ketone because of that. So yeah, that's always the case. Secondary alcohols, no matter how much there is, always going to end up as a ketone. If it's a primary alcohol, will always end up as a aldehyde.
Got it. Thank you.
Other questions? Okay, so again, we could take a look at another one. Why don't you try this one here? Let's do a couple here just to make sure. I'll do this guy. That's not what I want to draw there. I'm trying to get. Take that off. There we go. All right. There we go. Let's do this, and I'll just not draw out the rest of it here. Do this. Do this. All right. Why don't you draw the product of that one, and why don't you draw the product of this one here? Just take a couple of minutes here and see what you come up with. Okay, so let's take a look here. And again, when you see your alcohol here, and you see the oxidation, really you should just not worry about anything else and know that, okay, I know that everything's going to happen right here between the carbon-oxygen bond, right? So you may want to sort of figure out first off as well what type of alcohol you're dealing with here. So if we look at this carbon that it's attached to the OH group, and it's attached to 1 and 2 other carbons. So this tells us it's a secondary alcohol. Just by our conversation a second ago, we know we now should end up with a ketone, really. So because I know that's pretty much where everything's going to happen, I know in these oxidation reactions, we're talking about losing H2, and I know it comes from the oxygen and the carbon. Pretty much I now have the product I need to draw. I could just copy it exactly the way it is. Again, we're going to do what we talked about, just make that without the hydrogens, obviously. We'll go here. By the way, I obviously have way too many hydrogens on those. Bad job there. All right, so we'll do that, and we'll do that, and now we'll do that. There we go. All right, we did a little fixing. Obviously, the H2 would come off as well. And what's the last thing we should do in this situation? We need to lay up a double bond, right, between the carbon and the oxygen right there. And there it is. There's our ketone. And in case you can't see the ketone part of it, ketone is a 3-carbon run, which is right there, 3 carbons, with a double bonded oxygen in the middle. So that's where the ketone part of it comes from. And again, you can see that the alcohol was interior, which means we end up with a ketone in this particular case. Any questions on that particular one there? Same approach as you look at this. I see an OH, I see an oxidation move. I know this is where I need to be focusing in on, and that's my carbon oxygen. I also know that I'm going to remove a hydrogen from the oxygen, And in this case, there's actually 2 hydrogens here, so we're going to take just one of those hydrogens off. That again will really produce my H2 that's going to come off. Everything else is going to remain the same. We're going to make that carbon oxygen a single bond. And don't forget, in this particular case, I'll just draw it to the left here. There's that second hydrogen. Remember, we're only taking one of those off. So we still do have a hydrogen there. Get rid of that plus kind of close. There we go. Now everything else gonna be the same. CH2, 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 and CH3. And here we made our aldehyde, and we know that because if we originally did this, this carbon's attached to one other carbon, means that this is a primary alcohol, should yield us an aldehyde at the end. And in this particular case, we need to finish it by making a double bond right there. And that would be our aldehyde group hanging out right there. Any question on those 2 reactions there?
I just have a quick question. Oh,
Yeah.
Sorry.
Whoever wants to go first.
Go ahead, Rebecca.
Oh, I was just curious if you can make the aldehyde into a carbonic acid.
You in this particular case, you wouldn't do that if you really did start with the alcohol and it just asked you to do the oxidation. This is probably what you should draw. If it then did something like another arrow and the oxidation, and then you would turn it in to your carboxylic acid, which basically just means we're just going to insert the oxygen there. Everything else will remain the same, exactly the same, other than we put that oxygen in. So if that's what you're asking, it would look like this if you're asking me to draw it. But it would happen, though, upon the second oxidation after you do your aldehyde.
Got it. Thank you very much.
You're welcome. Was there another question?
Yeah, I was just curious. The H2 on the reaction side,
Yeah.
does it matter if it goes in front or behind?
Like how I put it here or here?
Does it matter?
It doesn't matter. As long technically, and sometimes people might not even write it in these things. They're more focused on the sort of ketone or aldehyde, but it doesn't matter as long as it's on technically the right hand.
Okay, thank you.
Welcome. Other questions? Okay, so while we're speaking about basically the hydrogen there, these are oxidation reactions going in this direction, going from our alcohols to our aldehydes or our ketones. With an oxidation reaction, there's always like a reduction reaction that occurs. And really the reduction reaction is actually these reactions going back in this direction. And they're sometimes labeled as reduction reactions. They're sometimes just labeled like H2 kind of up there. And that's because, again, a reduction reaction is the addition of hydrogen. So you may wonder how hydrogen gets us back to this, and it really is the reverse of what we just did. So I'm going to just start with, I'll start with the ketone that we had up there, for example. And basically what I'm going to draw is really the reverse reaction, which is the reduction reaction that occurs. And you could think about the reduction reaction, it's adding H2, right? So basically H2. And you could think about this reaction as almost identical to what happens when we add H2 to a double bond. When we add H2 to a double bond, this double bond becomes a single bond, right? And we put those hydrogens on. And the exact same thing happens here as we go through the reduction reaction going backwards. And if you look at our ketone or you look at our aldehyde, there's only one place where there's a double bond, and it happens to be right here, right? So even though these are not 2 carbons with the double bond, it actually works the exact same way. So what did we do here? We made the double bond into a single bond. So if we were to do any of these reactions going in the reverse direction, which would be the reduction reaction, we would basically follow exactly what we do with a double bond that you add H2 to. This entire molecule is going to be exactly the same. Nothing's going to change other than we're going to, in this case, remove the double bond. So if we did that, we would end up with this now becoming a single bond. And the reason we make it now a single bond going in this direction is we want to add a hydrogen and a hydrogen, and we need room. And they get added exactly the way we add hydrogen. One goes to one spot where the double bond was, and I'll just draw it here. The other goes to the other spot. And that would be these two hydrogens that we just put on. And what do we end up with? We got back our secondary alcohol. Exactly the same thing that's up here, except I drew this H out, but it's basically the same. So an oxidation going from a primary alcohol takes us to an aldehyde. If you then do an aldehyde reduction, it actually takes you back to the alcohol. And same thing with the secondary alcohol. If you oxidize it, you end up with a ketone. And if you take that ketone and put it through reduction by adding H2, it takes you back to the secondary alcohol. So they're kind of back and forth reactions. Any questions on that? And that's essentially the same thing that you see here with our primary. If you just imagine we're going to put an H onto this guy, H onto this guy, make our double bond a single bond, we're back over here, basically to the guy on the left. So again, the importance of this is just one spot is where all this change occurs, and it's always at just one spot. Any questions on the oxidation of a primary or secondary alcohol? And again, for clarity, going backwards, putting the H2 back on is not an oxidation reaction. It is a reduction reaction that's happening. Now, what about our tertiary alcohol? Well, if you remember, our tertiary alcohol here means that this carbon is attached to 1, 2, and 3 carbons. And if you remember, the oxidation reactions we've been talking about requires the loss of 2 hydrogens. So when a tertiary alcohol tries to go through oxidation, it could get halfway there in the sense it's got 1 hydrogen, but it is missing that second hydrogen that's on the carbon. And because it does not have that second hydrogen, you will get no reaction. It will not go through an oxidation. So no reaction will occur with a tertiary alcohol because it's missing that crucial second hydrogen on the carbon there. So that's a simple one. No product is made in that case. So if you have an alcohol, you do an oxidation reaction or try to do an oxidation reaction and you don't get a product, then you know you have a tertiary alcohol. Question on tertiary alcohol. So I think we talked maybe about some of these guys, but here's some methyl alcohol, which is methanol. This again being oxidized to a aldehyde. And again, our aldehyde getting oxidized to our carboxylic acid. So same idea here. If you just kind of count what's going on, first guy is our loss of hydrogen. So we lost 2 hydrogens there, leaves us 2 on the carbon, which is our 2 here. Oxidation of our aldehyde takes us to a carboxylic acid by the insertion of a oxygen there. Here's some ethanol, which is ethyl alcohol. And again, we see the same sort of oxidation occurring in this case. And again, we get our aldehyde here. This guy actually breaks apart into CO2 and water through that carboxylic acid that's made, which is basically ethanoic acid, and it kind of decomposes into CO2 and water. All right. Any questions on alcohols? I think that pretty much wraps up alcohols. Okay, then we're going to move on to another group of organic molecules, and I'm imagining by the picture of the skunk, probably things that don't smell so good, but these are thiols, and thiols are really sulfur-containing groups. They're kind of very similar to alcohols. If you even look on the periodic table, right, oxygen's here, sulfur's there. So they share very similar sort of properties kind of with alcohols. It's also a polar group as well. But anything that involves sulfur usually has a pretty bad smell, and that gives us our sort of thiols here. You don't have to worry about naming thiols for me, but we'll just kind of talk really briefly about how you go about naming them, just so you have a sort of an idea. The way we go about naming thiols is kind of just take the longest carbon group and really keep the name. So that's methane, right? 1 carbon. So you can see methane is here, and then you just kind of put thiol at the end. So that's methane thiol. Here we have basically 2 carbons, which is ethane, and you put the thiol at the end. Here the longest group is 4 carbons, which is based off of butane. You put the thiol, and kind of like the alcohol, because there's more than one option, we give the location of where that is located, and that would be 2-butane thiol. So for us, you don't need to worry about naming thiols. You need to know the functional group of a thiol, which is SH. And we'll talk about a reaction, I think, of thiols a little bit later, but we need to know the reaction that happens with thiols. And just to preview that reaction, when you put 2 thiols together, it actually will go through a oxidation reaction. Oxidation reaction meaning we are losing 2 hydrogens, right? And basically it makes a bond that you might be familiar with, and we'll see it a little bit later on. It makes this bond, which is sometimes referred to as a disulfide bridge or bond. Happens a lot in sort of proteins and stuff like that. But it's basically, again, a loss of that H2, like we were talking about with the oxidation of alcohols. H coming off of one thiol, H coming off the other thiol, making this disulfide bond bridge. Obviously, at the end of this would be some carbons, you know, so if you had something like this plus something like this, and we kind of put them together, we're simply just going to take out the hydrogen, makes it our H2, and honestly, the rest of it, you just squeeze together. You just start to the left, go to the right, and just take out the 2 hydrogens. So go to left, now take out the 2 hydrogens, go to the right, and that's your product right there. So thiols you do need to know this reaction. I think we'll see it maybe again a little bit later on, but you need to know that the SH group is a thiol, and this pretty much reaction here where you basically take out the hydrogen and slap everybody together, just squeeze them together, and you get the end of it. Any questions on that there? Okay. And we're not going to worry about, again, the naming. The next group that we're going to talk about, though, are ethers. Ethers have a functional group of carbon, oxygen, carbon. So that's sort of the functional group of an ether. And basically, when we name ethers, we're going to go with just like the common names, not maybe the IUPAC way of naming. So more of a common way of naming. And the common way that we name ethers is not too bad. You pretty much get yourself an ether happening. However you get yourself an ether happening, I suppose. And you get that guy going on there, right? And the common way of naming an ether is to simply go to the oxygen. And then what you want to look at is what group do you have to the left of the oxygen? So if we come over here, we got 3 carbons. 3 carbons is based off of propane, and it's a group that's a propyl group. Then you go to the right of the oxygen and see what group you got going on there. That's a 2-carbon group, which is a ethyl group. And then you put it in alphabetical order. So that means we would call it ethyl propyl, and then you simply put ether at the end. So that would be ethyl, if I put the L in there, ethyl propyl ether. Basically, go to the oxygen at your center point, go left, go right, find the groups that are located there. Again, we see our ether on the bottom here. And to show you how we get to that name, we go to the right of the oxygen, that's a methyl group. We go to the left of the oxygen, that is also a methyl group. Just like we've been doing before, if we have 2 methyl groups, that is what is referred to as dimethyl. And then we simply put ether at the end of it. So dimethyl ether would be the common name for that. In case you're curious what the IUPAC name would be for that, it is what is known as methoxymethane, which is why we much prefer these common names for this guy. How you get methoxymethane is longest carbon group is 1 carbon, which is the methane part. This guy, we drop the YL part of it for methyl and put oxy on it, and that's where the methoxy part comes from in that particular case. This guy up here would be ethoxypropane. Again, propane being the longer group, this guy being the shorter group. So you can see it's much easier and much better to go common names. And for us, that's what you'll be required to know, is how to name it common way, which again is to go to the oxygen, go to the left, go to the right, name the groups, put them together in alphabetical order, and then just simply put ether at the end of it. Any questions on that there? And that's sort of what I just did, almost similar example. But again, here, if we look at our oxygen as sort of our center guy, to the right, we have a propyl group. To the left, we have a methyl group, alphabetical methyl before propyl, and simply place ether at the end of the name. So not too bad. It's sort of the common name that's used for that one. Ethers are used obviously for anesthetics that put people to sleep, basically, and that type of stuff. A lot of times over the years, they have sort of substituted out a lot of fluorines, found to have a little less side effects than hydrogens and some of these things, and kind of used in that sort of process as well. All right, so why don't you take a second and draw the structures for these guys: 3-pentanol, ethanol, and diethyl ether, and see what you come up with. Okay, so we want to draw the structures here. So again, as we've talked about, we always want to work backwards in the name. So it does tell us a couple of important things. First off, we see the OL, so that should mean alcohol. That means it should have an OH group. Pentane part of it tells us it's 5 carbons, and the 3 in this case would be where the location of that OH group would be. So just like normal, we want to just start with sort of the skeletal structure here. We're going to lay up 5 carbons. In this case, you could call the carbon on the left number 1. You could call the carbon on the right number 1. I'm going to call the carbon on the left number 1. And that means I need to go to carbon number 3. And in this case, that is where my OH group would be located. Everybody else, just like we've done before, are going to be hydrogens until we get to 4 bonds for carbon. And this guy needs a couple, and this guy needs 3. There it is. Any questions on that particular one there? We haven't done line structure in a bit, but if we did sort of a line structure, 1, 2, 3, 4, 5, I think 1, 2, 3, 4, 5, and a carbon number 3 would be my OH. It would look something like that, by the way. Any questions on that? Ethanol, we work the same approach here. So OL again tells us it's an alcohol. Again, should have an OH group. Ethanol tells us it's only 2 carbons. I don't see a number there, which implies that it doesn't matter where I place the OH because it's always going to be on the right carbon. So same idea, we're going to do actually 2 carbons here. You're going to put your OH really at carbon number 1, which could be on the left-hand side or the right-hand side. And then we're going to finish it out with some hydrogens there, like something like that, I think. Any questions on that one there? Now we're going backwards here and we see ether. Ether tells us it is an ether, obviously, which has a functional group that looks something like this. So this tells me that I have a carbon-oxygen-carbon connection that's happening in this molecule. We also just talked about that this is going to be like the common name, which means diethyl. And that means that I have basically di is 2, and I have two carbon groups. That is a mouthful. Two carbon groups happening here. And again, looking something like this. So the importance of understanding the functional group here is it helps us with the connectivity, right? So I know simply I could draw one of these ethyl groups coming in, and I know the connectivity here is going to be an oxygen, and that's going to be connected to the other group on the other side. And I could put it in just like so. Any questions on that one there? So again, kind of important to make sure you understand the functional groups. You do need to know the functional groups, but it can also help you sort of visualize, if you will, sort of what the structure should look like by understanding and kind of knowing what those functional groups look like. Any questions on any 3 of those there? Okay. Obviously, some properties of alcohols, as we talked about, alcohols are very soluble in water. 6 or less carbons are soluble in water. Alcohols we're talking about here. Again, for us, what we talked about at the very beginning, having that OH group in the alcohol able to interact really well with water, which also, again, has that OH group, and that negative, positive hydrogen bonding, which is a very big key here, and a lot of solubility in organic chemistry, hydrogen bonding between that and water. Again, though, as you get above that 6 carbons, decreases the solubility. What can increase the solubility is actually if you actually have more OH groups on the alcohol. Some alcohols have a bunch of OH groups on it, and that definitely increases the solubility of it in water. So for example, if you had an alcohol where, on both ends, for example, there's an OH group, this is going to be very, very soluble in water because it has multiple places where it can interact with water and make it very soluble. We don't worry about the names or anything like that for these type of guys, but there are, again, some alcohols that actually do have multiple OH groups on them. And again, that definitely does increase the solubility of it because everywhere there's essentially an OH group, it does allow it a place to interact well with water and be soluble. Guess I jumped the gun earlier, but again, we talked about this. This is, again, classifying our alcohols as primary, secondary, and tertiary. And it's always the carbon that has the OH group is the one you want to analyze and how many carbons attached to it. So that's 1, again, the carbon with the OH group, 1 carbon, 2 carbons, secondary, carbon with the OH group, 1 carbon, 2 carbons, 3 carbons, again, our tertiary alcohol. So why don't you take a second here and classify each of these as primary, secondary, and tertiary. Do as simple as counting secondary. Here, this is the carbon that has the OH group attached directly to it. 1 other carbon makes it a primary. And lastly here, our carbon here that has the OH group attached 1, 2, and 3 carbons directly to it is a tertiary. So again, that's a very important thing to understand, the classification of alcohols, as we just saw with the reactions, to understand what you should be producing, right? If you start with, say, a primary alcohol versus a secondary alcohol versus a tertiary alcohol, what you should be producing. Any questions on that there? So as I was talking about, again, alcohols are pretty soluble in water. Again, it does start to decrease as you increase that sort of carbon chain, and it's a process of why it decreases, because if you look at this guy versus this guy, they're both alcohols. They're both primary alcohols. But this guy is soluble in water because it's relatively small, which means, when water is coming by, it doesn't have a problem sort of finding it. When we increase this part, which by the way is carbons and hydrogens, it increases the nonpolar part, if you will, of this alcohol. In addition to that, it's fairly large, which means it creates what is sometimes referred to as steric hindrance, which is a big word that says the thing gets in the way. So this big part of it, right, that's nonpolar, and we have this very small part that's polar. And in this case, when water is floating by, it's like, I don't really see anybody I can interact with. I don't want to interact with this part of the alcohol because it's nonpolar. Remember when we talked about solubility, like dissolves like, which means things that are polar and polar are very soluble in each other. Things that are nonpolar and nonpolar are also soluble in each other, but things that are polar and nonpolar are not soluble in each other. So water coming across this sort of nonpolar side of the alcohol, not going to allow it to interact really well. It's got to find its way over here to this really small part that's kind of being hidden by this larger part. And it has a dramatic effect on the solubility. And it really does start to decrease a lot, again, as you build out sort of those nonpolar part being bigger and bigger. And that's what we see. And that's sort of what we talked about, less than 6 carbons, even maybe less than 5, they're fairly soluble, but you can see a sharp decrease in sort of solubility as you head in this direction. And what's happening as you head in that direction is the nonpolar part of these alcohols are getting larger and larger. And again, almost creating like a barrier and allowing really the water and the alcohol to interact, or the OH part of the alcohol to interact. Any questions on that sort of solubility there? Obviously, hand sanitizers contain ethanol or propanol as sort of their active ingredient. We've all been using a lot of that lately. Obviously, 60% by volume or 85% by volume works really well, obviously, hopefully, in disinfecting and killing some growth. Also very flammable as well. So be careful on that stuff when you use it. Solubility of phenols. So if you remember, we also talked about phenols, which are alcohols, but they contain a benzene ring, and they're also slightly soluble in water. They can react with water, producing a hydrogen bond, and they react almost like an acid-base sort of reaction, where that acts as an acid, this guy acts as a base, and obviously we create like H3O plus here and O minus in this case. So almost very much like a acid-base sort of reaction, and with the donation or protonation of the H plus over to water, making H3O plus. You don't have to worry too much about that reaction, I think, for us. So let's take a look at each of these and decide whether each of them would be soluble in water and not so soluble in water. So if we look at sort of this group, they're both alcohols, right? They're both actually primary alcohols, right? Primary alcohols, each of these guys are connected to one. Again, we would anticipate this guy here being soluble. It's small, it has that OH group. But remember, right around that 5 to 6 carbons is really when we start to see sort of it becoming more insoluble and not really mixing. And again, here we got 1, 2, 3, 4, 5, and 6 carbons. It's just for the fact, as we were just talking about, that we basically have built out this big non-polar part of this alcohol. And again, it just leaves a very small opportunity for this guy to interact well with water. Remember as well, when we talked about water and sort of its solubility, in order for things to be soluble in water, you know, you have to replace kind of water-water interactions with similar interactions. So water is a relatively small molecule. So if you try to replace that with something that has a big old sort of carbon hydrogen part to it, it's just like no room for it. It's kind of like when we talked about oil and water, right? It's basically all carbons. You know, there's kind of no real good room for it to kind of fit with all the other water molecules. There's not a lot of interaction happening because of that big guy. And again, it just really does decrease the solubility a lot. Any questions on that there? Our alcohols. Okay. The next sort of organic groups we're going to talk about are two that are sort of related to each other. And we actually saw them a little earlier today in the results of the two reactions that we talked about, aldehydes and ketones. So we already know right off the bat that if we take a primary alcohol and we oxidize it, we're going to hit ourselves an aldehyde. And if we take a secondary alcohol, as we talked about earlier today, and you oxidize it, you're going to hit yourself a ketone. What are some of our functional groups here? As we talked about, they both revolve around the carbon-oxygen double bond, but our aldehyde, as we saw earlier, carbon-oxygen double bond and a hydrogen is the functional group. While our ketone is what I was talking about earlier, sort of our 3-carbon run, where you have the double bond right there in the center of those 3 carbons. And that again would be our functional group of our ketone. The simplest ketone is basically acetone or propanone. It is obviously used to remove certain things like paint, nail polish, and all that kind of stuff. So let's talk a little bit more about some of these. They both really contain this carbonyl group. And when we talk about what a carbonyl group is, it is this guy right here. It is the carbon-oxygen double bond. So carbonyl group, this is sometimes referred to as the carbonyl carbon because it's part of that group. But it's a carbon-oxygen double bond. Now, if you think about polarity and bonding, if you think about where carbon and oxygen is on the periodic table, carbon and oxygen are in the same row and oxygen is further to the right on the periodic table, which means oxygen would be more electronegative than carbon, like we talked about when we talked about bonding. That means that it is a polar bond between the carbon and the oxygen, creating a partially negative charge on the oxygen and a partially positive charge on the carbon in this particular case. So we do have that sort of strong separation of charge that occurs in that particular case. And both of these organic groups really do contain that sort of part of it as part of its functional group, that carbonyl group, again, giving us our aldehyde functional group here, which in line structure looks like this. Again, a carbon is here. And our ketone, which in line structure looks like this as well, our sort of condensed structure over here. Now, what is the deal with sort of these groups and sort of where they are in the molecule? Well, another important thing that we talked about when we talked about bonding was the idea that our good friend hydrogen should only have 2 electrons, which means it should only have 1 bond, which means just like in regular bonding, hydrogen should always be at the end. And because the aldehyde group, functional group is this group will always be at the end of the molecule. It can never find itself in the middle because there's a hydrogen. And if you put them in the middle, hydrogen then has way too many bonds. and you'll never find the aldehyde group in the middle. That's different than the ketone. It's actually the opposite. Because the ketone needs that 3-carbon run with the double bond in the center of that 3-carbon run, you'll really never find the carbon-oxygen double bond in the end. It's always got to be at these, like in the middle of the molecule somewhere. Not dead middle, but it can never be at the extreme ends where we have our carbon-oxygen double bond in our aldehyde group. And that's actually really important in terms of naming these guys and how we go about naming these guys based on sort of where they end up, these sort of functional groups within the molecule. Any questions on that there? So also a couple of things. Sometimes aldehyde groups may be written like this in sort of condensed formulas. So if you see something written like that, it is implying the functional group for the aldehyde. And again, sometimes that carbon-oxygen bond may be written like that. Most of the time, people will kind of draw it out rather than sort of write it like that. I would say most of the time people will draw it out, even like this, very, I don't think you see it all that much. Most people would probably draw it like this, but you may see it written like that. And again, probably 99 times out of 100 people are probably going to lay up this structure here rather than writing CHO at the end of it. So it's good to know that those are sometimes sort of abbreviations that are used in condensed formula, but most of the time people, you know, sort of draw out that functional part of an aldehyde and ketone, even if you're doing sort of condensed formula like something like this. You know, it's very common people will sort of draw those guys out and stuff like that. Obviously in line structure, we incorporate the double bond and the hydrogens so that we can kind of make sure we understand. In the line structure, you would need to put the hydrogen because if you drew something like this, it actually would imply that there's a CH3 group at the end, right? Which is actually now a ketone, like it is sort of over here. So if you're doing line structure and you want an aldehyde, you do have to lay up the hydrogen there at the end of it, so it's understood that it's not a carbon and it is an aldehyde. Any questions on that there? All right, so then let's talk a little bit about naming aldehydes. And aldehydes are, you know, fairly simple to name in the sense. It's pretty much like everything else. We're going to be looking for the longest continuous carbon chain. Obviously, the longest continuous carbon chain does need to have the aldehyde group part of it. So what we do is we actually drop the E off of the alkane, and not to be confused with alcohols, this guy actually ends in Al. There are some common names that are used, and this is formaldehyde, acetaldehyde, propanolaldehyde, butyraldehyde. You know, formaldehyde is basically 1 carbon, and it looks something like this. Let me actually draw it correctly there. There we go. And then H. So this is basically based off of 1 carbon, which is methane. We drop the E, and this is what is known as methanal, Al. So not OL, but Al, methanal. Methanal is also what is known as formaldehyde. Perhaps you're familiar. Maybe you've taken biology or something like that. So formaldehyde is basically methanal, which looks like this. If we got to say 2 carbons here, one, 2 carbons based off of ethane, drop the E, becomes ethanal, Al. Now you may be asking, do I have to, like I did with double bonds or triple bonds or OH groups, do I need to give the location of where I find this sort of functional group? And it's a good question, and the answer is no, you don't. Because as we just talked about a second ago, the only place that that group can end up is at the end. And because of that, you do not have to give the location of where you find that group when you're dealing with aldehydes. But you should note that, let's just do one real quick here to finish up. Yeah, let's just do like a Cl, for example. Throw a 2 there, or throw a 1 there, or throw a 3 there. If I were to go name this guy, we would do our longest carbon chain that has the functional group in it, which would be straight across in this case. We would look at it and go, how many carbons do I got? 1, 2, 3, 4 carbons. 4 carbons is based off of butane. We drop the last part, it becomes butanal, AL. Now, the important part is you don't have to give the location of where that carbon-oxygen bond is, but because it is the functional group, it gets the priority, which means that wherever this carbon-oxygen double bond is, will always have to be carbon number 1, which means this would be carbon 2, this would be carbon 3, and this would be carbon 4. So although we don't need to give it in the name, it still takes the priority in terms of numbering. And that's important because now our chlorine is actually a carbon number 3, and this would be 3-chloral butanal. Any questions on that one there? Okay, any questions on whatever we talked about here today?